Welcome to part 3 of the Raymarching Shader in Unity tutorial by PeerPlay. In the previous part we've set up the camera frustum and visualized the ray directions as colors in the shader. In this part we will write the distance estimator sphere tracing. With this distance estimator we can start visualizing 3D environments that we can write in a distance field. Creating these free tutorials takes a lot of time and effort, and I couldn't have created these without the support of all the amazing patrons at my Patreon. If you find the contents of my tutorials helpful, consider supporting me at Patreon. In doing so, you not only support me creating these, but you get access to the source files, exclusive tutorials and extra content. Special thanks to MR, Andrew Laboy, Devin the Dude, Derek Fegter and Patrick Nugent. In the previous part we've created a variable initiator to get the world space position of the camera and set this through C#. Someone commented in the video that we can also use the built-in shader variables that are included in the Unity cg.cg include. We'll quickly change this as this is a little bit faster for the CPU. In the Unity documentation you can find the built-in shader variables that we can use, and if we go to the camera and screen we can find here the variable name world space camera pos. So let's copy that. Now let's open up the Raymarching Shader and we can delete this cam world space float 4. Now scroll down to where we implement the cam world space, which is here, and we'll change this to the world space camera pos. Let's save this and go to the C# script, and we can delete this line and save that as well. And with that in place, everything still works perfectly fine. Now we're going to create the sphere tracing system in our shader that I visually explained in part 1. We will march along the ray direction from the ray origin. We need to keep marching until we are inside a volume that we can specify in a distance field. We will start writing in the frag of the Raymarching Shader. Currently we are returning a fixed 4, which is the ray direction. Now instead of returning a fixed 4 color directly, we will create a function called Raymarching that returns a color. So above the frag we're going to create a new fixed 4. And we'll call this Raymarching. Now to do our Raymarching we need to get the ray origin and ray direction. So we're going to input here a float 3 and we'll call this RO for ray origin, and we'll get another float 3 and we'll call this the ray direction, RD. Now we need to call the Raymarching function inside of our frag. So underneath the ray origin we're going to create a fixed 4 and we'll call this the result. And that is going to be the Raymarching, and we'll input here the ray origin and the ray direction. And instead of this we're going to return the result of the Raymarching. So the Raymarching is a fixed 4 and needs to return a fixed 4. So the first thing I will do is to create a fixed 4 and I will call this the result, and that is going to be a fixed 4 1 1 1 1 1, and all the way at the end we need to return the result. To implement the sphere tracing we need to create a for loop so that it will move forward along the ray until we have hit something. We want to limit the amount of iterations in this for loop, so let's create a constant integer for this. So let's create a constant integer and we'll call this the max iteration. And we're going to set the max iteration to 64. Now if you have very complex structures in the distance field you might want to put this number a little bit higher, but for now this is perfect. The next thing we need to keep track of is the distance traveled, and for that we need to create a new float. So let's create a float and we'll call this float t, and we'll set this to 0 at start. So this float is the distance traveled along the ray direction. Now let's create a for loop. So for int I is 0, I is less than the max iteration, I plus plus. First we will set a maximum distance to travel for the rays that don't hit any surface. By setting a max distance we optimize the calculation time of the shader. And for our convenience we'll create a variable max distance that we can set in the inspector. So let's scroll up. And we're going to create a uniform float and we'll call this the max distance. Now let's copy this, and we can implement that in the for loop. So we're going to say that if t is greater than the max distance, then we're going to draw the environment. So we'll call this environment. So these are all the arrays that are missing anything to hit. And for now, we're not going to create an environment, but let's return the ray direction color. So we're going to say result is fix4 of the ray direction 1, and then we'll break out of the loop. Now if the current distance traveled is under the max distance, we're going to continue the for loop, and now we need to get the current position. So we'll create a float3, and we'll call this p for position, and that is going to be the ray origin plus the ray direction multiplied by the distance traveled. Now here we're going to check for a hit in the distance field. So check for a hit in distance field. And now we'll create a distance field function. So above the Raymarching, we're going to say a float, and we'll call this the distance field. And that is going to input a position. So we'll type a float3, and we'll call this p for position. Now in the for loop, we're going to say that float d for distance is going to be the distance field with the position of p. Now if the result of d is going to be minus, then we are inside something, and if we're above 0, then we are outside something. So we need to check that. So if the distance is smaller than, and I'm going to set it to 0.01, so we're very near to something. So this if statement is basically saying we have hit something. And inside this if statement, we can do the shading. Now in the next part, we will calculate the normals in this if statement and also add a Lambertian lighting model. But for now, I'm just going to draw a white color when we've hit something. So we're going to say that the result is going to be a fix4, and we'll set this to 11111, and then we're going to break. Now if the distance traveled is not above the max distance, and if it's not below 0, then we're going to add to the travel distance. So we're going to say t plus is d. Now at this point, the distance field is empty and we won't see any result. So let's put something inside the distance field to visualize that. And in a later part, I will discuss the distance field in greater detail, but for now I'm going to create a sphere. So to create a sphere, we're going to create a function called sphere. So we'll create a float, and we'll call this SD sphere for signed distance sphere. And the sphere is just a position and a scale or radius. So let's input a float3, and we'll call this p, and we'll use a float, and we'll call this s for scale. Now to create a sphere in the distance field, all we need to do is to return the length of a vector, and that is the current position, and we're going to subtract from that the radius. Now we can use this primitive inside the distance field, and in the distance field we'll create a float, and we'll call this sphere1, and that is going to be SD sphere, and we need to get the current position minus a certain position, and I'll just put in here a float3, and I'll set this at the center. And we need to get a radius. I'll set the radius to 2.0. Now we still need to return this, so let's type return the sphere1. Now let's save the shader and go to the Raymarch camera script, and in here we're going to add the max distance float. So let's create a public float, and we'll call this the max distance. Now we're going to set this max distance to the shader. So we'll say Raymarch material dot set float, and we're going to set the float in the shader of max distance to the max distance of this script. Now let's save this script and go back to Unity. Now back in Unity we only see the ray direction colors, but once we set the max distance to a higher number, then we can see the sphere. And I rotated the camera to 90 degrees in its y-axis and set the position to -4. Now this renders as a circle, but it's actually a 3D sphere, but it doesn't have any shading yet. And that's what we're going to do in the next part. Now as a little extras, let's say that you want to set the radius of the sphere or the position of the sphere to something else. And you don't want to go back to the shader all the time to change the variables in the shader. We can also create a public vector 4 in which the x, y and z components will set the position of the sphere and the fourth component will set the radius of the sphere. So let's do that. Let's go to the shader. Now let's go to the top of the shader and we're going to add a uniform float 4 and that will be called the sphere 1. Now let's copy sphere 1 and scroll down to where we've made the sphere in the distance field. And instead of this position, we're going to change this to the sphere 1.xyz. And the scale is going to be the sphere 1.w. Now let's save this shader and go to the Raymarch camera. And we're going to add a new public vector 4. And we'll call this sphere 1. And I will send this vector 4 to the shader. So let's say Raymarch material.zVector. We want to set the vector of sphere 1 to become sphere 1 of the script. Now let's save this and go back to Unity. Now you'll notice that the sphere disappeared, and that's because the sphere variables in the inspector are all set to 0. So if I change the W, which is the scale, you can see that the sphere appears again. And we can set the position to anything that we like. That's it for this part. In the next part we will calculate the normal directions of the distance field results. We will use those normals to create a Lambertian lighting model so that we can see the sphere as a 3D object. For now I want to thank you for following this tutorial part. If you found this tutorial helpful, feel free to like or share this video. To stay updated to new release parts, subscribe to the channel. Happy coding!